All right, so it's a great pleasure for me to introduce Professor Joseph Cusumano. Professor Cusumano is in the Department on Engineering, Science, and Mechanics at Penn State. He previously was at Cornell for some time, where he did his PhD in Theoretical and Applied Mechanics. He also had a master in applied mathematics from Brown, and also a bachelor in mechanical and aerospace engineering from Cornell. So Professor Cusumano research is, I would say, spans several fields in mathematical methods in the engineering and movement sciences. And today he's gonna give an interesting presentation on goal directedness and the control structure of human walking. So without stealing further time from Professor Cusumano, I give the stage to him.
Okay, well, thanks everybody. Thank you, Alessandro, for having me, and Kathleen for inviting me. My goal today is to I want to construct a story of a whole line of research that spans, I don't know, like a half dozen papers. So there's not going to be, even though it's mathematical, I'm not going to have a lot of math in the talk. I'll have mathematical concepts, but I'm mostly going to talk through it all, because what I really want to do is try to weave together the through line that goes from some experiments to some modeling work. So as you could tell from the title, the basic point of this talk is that I believe goal directedness is a crucial part of motor regulation, not just in walking, but in general. But the focus of this talk is on work I've done with John Dingwell since about 2010, mostly on walking, but not exclusively. But today's talk is focused on walking. So it's going to be split into two parts. So this is an empirically grounded, I think of it as an empirically grounded modeling effort, but we really started with lots of empirical studies, and we developed some model-based data analysis methods. And then the second part, I'm going to talk about actual first principles models. So the beginning here is the empirical evidence for goal-directed regulation. And the very first kind of thing I want to talk about is sagittal plane stepping on a treadmill. And I want to contrast our perspective with an energy minimization perspective. Sometimes people are surprised because I am a theoretical mechanics guy, and mechanicians and physicists in general, energy is very important. But in my opinion, a lot of the studies and theorizing on walking is overly focused on cost of transport and things like that. What I'm showing here is a picture from a paper that really the first paper in this line of work that John and I did, where we're showing energy contours that we got from actual humans, but we used an empirical formula for energy cost of transport. And then we're showing the stepping variance, a bar plot of stepping data for a person that goes on top of it. And the point is energetics, finding that minimum, which is in the middle of the picture, in the middle of that bullseye picture, it explains something like preferred walking speed, but it doesn't really explain how you're adjusting things from step to step. I'm not saying it couldn't in theory explain it, but I don't believe it does. And one of the reasons I don't think that, and in fact, the biggest reason, is if you actually look at stepping observables. So in this case, it's a sagittal plane walking. So I'm plotting step length and step time, which would be your main observables that you're looking at. Of course, you could say step, where do the feet go, where it's the step positions, but those are being broken or used to get step length and step time. And the diagonal line here that you see, can you see my cursor, I hope? Okay,
Yes.
I'm hoping. Okay, good. So that diagonal line is basically L over T is the treadmill speed. So that diagonal line is the treadmill, is the slope. The slope is the treadmill speed. And you're seeing that the scatter plot of the stepping lengths and times are falling right around it. And if you zoom in on it, this is normalized, but that's not very important for what I'm talking about. You're seeing that the data is scattered around that constant, that treadmill speed line. And that line is a goal equivalent manifold, assuming that you're trying to match the treadmill speed. And the idea would be that any point, if what you're trying to do is match the treadmill speed, any point on that line is fine. You don't care. There might be other reasons you would care, such as you might have range of motion limitations or things like that. But in terms of matching the treadmill speed, at least in some range, any point on that line is goal equivalent. And then tangent to that, you have this unit vector ET, which represents the tangent, and the perpendicular vector EP is off of the manifold. And so deviations in the perpendicular direction are causing changes in your step speed. Deviations along it cause no changes. And our basic thinking is very influenced by the work of Todorov and Jordan from the early 2000s on the minimum intervention principle, or what I just like to think of as the principle of maximum laziness, which is you don't bother to change things that don't matter. Okay, if something isn't, if you're trying to do something and you could change your posture and it doesn't affect your ability to perform, you don't care. You're not going to try to control that. So that's the minimum intervention principle. And in this particular case, if I'm controlling speed, if I want to match the speed of the treadmill, I would be on this goal equivalent manifold, which in this case is just a line. And this is at the task level, or the end effectors. In other words, this is the output of the neuromotor system generating the movement, and I'm just looking at these output observables, length and time. Now, we can analyze data like from this, and up here in the upper left is just another one of those scatter plots of stepping time series. And below is variance. And so what you're seeing is the red is the tangential direction and the blue is perpendicular. And you're seeing that the variance, it's the variability cloud is longer along the GEM, goal equivalent manifold, and smaller perpendicular, or the variance is smaller perpendicular. In other task manifold methods, such as the UCM, or really any of the task manifold methods that you might have heard of, they tend to emphasize this geometrical structure of the variance ellipsoid. And they'll say, oh, well, the fact that it's more scattered, more spread out in this direction is evidence supporting the idea that you're controlling the speed. But something that has always set John's and my work apart from those other methods is we're very interested in the dynamics from step to step. And so we look at not just the spatial statistics of the variability ellipsoid here, but we're also looking at the corrections from step to step. And one way to do that is if we look at the tangential and perpendicular time series, you'll see that the tangential one, it's drifting around a little bit more, whereas the perpendicular one, it's closer to like a white noise kind of signal, okay? And is there a way to quantify that? And the answer is yes. You could do detrended fluctuation analysis, which is a whole can of worms in itself. I believe a lot of that work that has been using it, and John and I wrote a paper on that. I don't think it's particularly correct. We use it in a non-standard way. We use it strictly as a test for persistence and as an indicator of what Roerdink and al. In 2019 referred to as our tightness of control interpretation. And it goes like this. Persistence is a property of a random time series such that if the deviation from the mean is in one direction at step k, it's in the expected deviation, the deviation is expected to be in the same direction at step k plus 1. That would be a persistent time series. You drift in one direction and you're going to tend to drift in the same direction at the next step or the next time unit. Whereas if you have a deviation from the mean in one direction at time k, and you have a likelihood of deviating in the opposite direction at time k plus 1, that would be called anti-persistent. And if if you have no preference in either direction, those are uncorrelated time series. So the DFA exponent turns out to be mapped onto those options in a slightly odd way. If you get a DFA exponent of 0.5, that corresponds to uncorrelated or white noise. And if you get a DFA exponent alpha of 1.5, that would be Brownian motion, a random walk. And so what you're seeing is that this red curve, we have a DFA exponent that's closer to a random walk. There's more drifting. There's diffusion and drift, if you are familiar with the language of random stochastic processes. So there's more drifting going on, whereas perpendicular, it's closer to 0.5. Okay. In fact, there's a little bit of overcorrection. It overshoots a little bit. So it's a little bit negatively persistent. Now we think this is, we interpreted this experimentally as indicating the strength of control, or what Roerdink et al. Called tightness of control interpretation. And the basic idea is, if you're off the manifold, you want to get back to it pronto. And so at the next step, you're pretty much bang on it. That would be DFA of 0.5. Whereas you have what I consider just to be lackadaisical or indifferent regulation along the manifold. So there's a bit more drifting. Okay. So this is purely empirical observation. Now, it's also, you could say, perhaps a little abstract, because it's using language of random processes in this unusual correlation measure of the DFA exponent.
Do you mind
So
if I ask you a question about the
please.
yeah, sorry. The on plot B, for example.
Yes.
I would have expected there was some sort of step-by-step negative correlation. In the sense that, you know, let's say I'm overshooting, then I have to undershoot the next step, and so on. On
That's
the
B.
delta T.
That's the blue curve.
That's a blue curve. That's the
Yes,
blue curve.
that's what this is indicating. There's a slight negative correlation because I'm overshooting perpendicular. I'm actually overcorrecting a little bit. Whereas in this direction, what happens, I'm going to show you more pictures, and I think
good.
that will be even better. But the idea is, along the gem, since you don't really, this is, now keep in mind, this is our interpretation, because it's just math. The math doesn't have an opinion about what it means. But our opinion is that when you have a deviation away from your mean, you know, preferred walking speed, say, in this direction, you don't immediately correct it because it doesn't change your speed. So you can drift a little bit along here, okay? And that's what you're seeing, and that's indicated as a DFA signature of a number closer to 1.5. In this case, it's closer to 1, okay?
Good, thank you.
Sure. Now, motivated by that, we attempted to construct very simple regulators using only the observables at the task level. So the observables that we're using are length and time. And to stay on the treadmill, what you have to do is you can't walk off the front or the back. And so this is the displacement of each step in the laboratory frame. You step forward by length L, and then you move backward because of the treadmill velocity V times T. And so this is the net displacement at each step, and the sum of all of those at time end you can't go off the front or the back of the treadmill. Any way you could do this would be okay. You can do all kinds of silly walks, right? I could stand motionless until I'm near the back of the treadmill and then leap forward to the front. I could do all kinds of things. But for steady walking, we hypothesize, well, you know, the simplest thing to do is to just set this to 0 every time. Then the sum of 0 is 0. So if you did that, that's equivalent to controlling your step speed at each step. Now, I emphasize, this is not a theorem, it's a hypothesis on the stepping dynamics, okay? So what do we do with that? we look for an update map. So these are the length and time column vector. We're looking for a controller that adjusts the stepping variables from step K to step K plus 1, and there's some noise. And what we do is we pick U so that it minimizes the expected value of this error function or cost function. Okay, we're just basically trying to drive this quantity to 0. And for these simple, super simple models, it's an undergraduate calculus exercise, especially, I mean, at least if somebody tells you some, again, introductory random process things, because you have to find expected values and stuff like that. But it's a very simplified, very simple model. Now, I'm only showing the error correction here. In the papers, if you look at them, we have you could add other costs. All of them would be hypothesized. You could try to fit data. But in this talk, I'm not so much concerned about fitting the data. I'm talking conceptually about, I'm trying to talk about the physical science here. So the emphasis is on basically minimizing the distance from the goal equivalent manifold. You could have other things. If you look at the papers, we have, like, for example, you could put the controller could have a cost. Too much effort is a cost. But what we found over time is that this is by far the dominant thing. When you do this, because this is a quadratic cost, you just get a very simple linear AR model. This is called a step, a single step update map. Just takes the length and time at one step to the length and time at the other step. Now, if we do this, I can compare the results to human data. So here's here's the human. This is the step speed. So this is speed control. And this is the step position. This is absolute position control. So I didn't show that in the previous slide, but you could have a similar cost for position. You could try to drive the position to the middle of the treadmill. Without loss of generality, you could just think of that as 0. You want to keep the position at 0. And that's an interesting thing in itself from this early part of our work, because it was a good criticism. People go like, well, of course you have to control the speed. You're on a treadmill. But other people will go like, well, of course you have to control the position. You're on a treadmill. And what I'm going to show you here is fluctuation analysis allows you, somewhat surprisingly, to distinguish between something that's regulating speed and something regulating position. How? Using our strength of or tightness of control interpretation. So if you look at the speed here, you're seeing this very rapid, nearly uncorrelated, somewhat close to white noise residual, or not residual, the time series of the speed. Whereas if you look at the position, it drifts around. Okay, it doesn't go off to infinity, but it drifts. If we make a position controller, so there's 2 position controllers and 2 speed controllers, I'm sorry, you can ignore, just think of one of them. It doesn't matter. For our purposes, it doesn't, they're slightly different. One of them is overcorrecting. That matches the data better. Not important for what I'm saying. This is a speed controller, just that simple AR model that's minimizing the speed. And I'm sorry, this is the position controller, P. And you have this signal for the speed, but then you have this very tight regulation of the position, as you would expect, because you built it into the regulator, right? And so the position controllers do that, but the speed controller, it controls the speed, but then you see some drifting in the position. This one, if you compare the red to the navy blue ones, they're closer together. Okay, they're more similar. They're qualitatively similar to each other. The statistical properties are similar, whereas the position controller does not have the same statistical properties in terms of as measured by, say, DFA. And there's another way we can look at that. We can look at the correlation between deviations at the next step and deviations at the previous step. So relative position here, P prime, is the deviation from the mean at step N. And if you corrected that 100% at the next step, the data would fall on this -1 diagonal. If we look at humans, they don't appear to be trying to correct the position at the next step. But if you look at the speed, they do indeed almost perfectly try to correct the speed at the next step. And our model of this happens to be the slightly overcorrecting speed model. You get a scatter plot similar to what the humans are doing, whereas the speed and furthermore, the speed correcting update model does a bad job correcting position. So the point is the speed qualitatively matches, the DFA matches, and the correlation between corrections match what humans do, whereas the position correction doesn't. It doesn't have the same qualitative characteristics. Okay, so that is the first evidence that we can use goal directedness and construct very simple empirical models of fluctuations that indicate what's being regulated. So the next...
Can I interrupt you one more time?
Please do.
So you consider autoregressive models of order 1, correct?
They're just order 1. That's correct.
But in principle, it could be that the effect is at lag 2 or 3 or 4 or whatever.
That is also true. So we're only doing lag 1 or single step models. Now, that is another interesting, that's a very good observation, right? I haven't done that. I've only partially done it. So you're correct. You could do something like the Akaoki information criterion or one of these things to try to estimate an ideal lag. However, I will say this. What happened is these single step models do such a good job that we were never really motivated to go that route because it just adds complexity. I do think it would be interesting. I will also add, however, that I think a theoretical work by Zaitsev and Ruina and I'm terrible remembering people's names. I'm a bad scholar. There's work that indicates, I'm thinking of eye tracking work that indicates that it looks like people aren't looking much more than 1 or 2 steps ahead. So, but I agree that you could definitely see if looking at higher lagged AR models helped. You could definitely do that. I don't think it's going to change this story though, but it would still be interesting.
Awesome. Thank you. Thank you. Great.
Okay, so now the next task is we wanted to actually look at the next study, we want to look at lateral stepping regulation. Now, you'll notice throughout this that I'm just decoupling sagittal and lateral stepping. That in itself is something you could dig into, but we're not the first people to do that. I mean, it's a very common thing because in the linear limit, if you think in terms of pendulum type models, they become uncoupled, the sagittal and frontal planes. Be that as it may, this is not anything in a linear limit, it's experimental. So we're just looking at lateral stepping. Now you have the left and right foot placements, and we're going to define the midpoint is ZB, which you can think of as a proxy for the center of mass position, horizontal, left to right, and we have the step width. Now, in these experiments, people were asked to walk on the path, so ZB is important for them to control. However, step width is known to be very important for stability, lateral stability, okay? So, oh, before I get to that. So here's just what some data looks like. If you look at here's the left is the left and right footsteps, then we have ZB and W. And if you think of the previous discussion I was having, you could see that ZB looks like it's not very tightly controlled because there's more drift, whereas W looks like it's pretty tightly controlled. And if we look at the scaling exponents, it's consistent with our interpretation, right? The alpha for ZB is 1.1-ish, meaning it's not strongly controlled, whereas the step width is closer to 0.5, indicating that it's barely persistent, okay? Suggesting more correction at each step. Okay. Oops. Okay, so in this case, we're going to construct the same kind of regulator. Now the observables are ZB and W, this position and step width. But the cost function is multi-objective. So I'm trying to minimize the step width at the next step, just a single step regulator again, from the target, which we take to be the mean, and the position from the target. But you can only put your foot one place. So we use a mixture model, okay? So rho is a mixture parameter. If rho is 1, it's entirely step width. And if rho is 0, it's entirely position. Now, we found by basically a trial and error adjustment of these simple models and matching them to the means and variance and DFA results, we found that rho equals 0.9 was a pretty good match. Another methodological thing, could we do something more precise like likelihood, expectation maximization? Yes, we could. We did not do that. I think that would be very worthwhile to do as well. But that's more of a precise thing. I don't care that rho is, I don't really care in this discussion if it's 0.85 or 0.92. It doesn't matter. The point is, it's predominantly step width control and a little bit of position control or regulation, okay? If we look at simulations of similar AR models that have that balance, you get stuff that looks like what the people are doing. And in fact, if you look at the standard deviations don't matter. We force those to match fairly closely. But the scaling exponents, which we don't really predict ahead of time, they work, okay? The scaling exponents are close to what the people were doing, and the for both the ZB, which is weakly regulated, and W, which is strongly regulated. Furthermore, if I look at the direct control plots, here's the humans. ZB correction, the direct control plot, you don't correct very strongly at all. Whereas W is corrected fairly strongly. The fact that it's a little bit less of a slope than -1, or bigger, I should say, than -1, indicates it's a little bit suboptimal in the positive direction. If it's overcorrects, the slope would be bigger than -1. But anyway, that's what the people are doing. That I'm saying it would be that according to our interpretation of control. And the model, as you can see, we kind of can match it that way. Okay, so, and then the last kind of plot that I think is interesting is to look at the gems. So if we look at the left step position and the right step position, every time you put a foot down, it's a point in this plane, okay? And there's a few things I want to point out. So the green curve is constant position line. If you were walking with constant position, you would be somewhere on this line. If you were walking with constant step width, you would be somewhere on the red line. Humans, the scatter plot looks like this. If we build a single objective regulator in position, we'll get data that looks like this. The model data, the simulated data will look like this. If we regulate only position, step width, we'll get simulated data that looks like this. When we have the 0.9, the 90% step width regulator, we get data that looks like this. So, and one last thing I want to say is, if you think in terms of principal components, you could see that the principal axes of this variability ellipsoid, and let me point at the data, in fact, they're kind of lined up with the ZB goal and the W goal, the position and step width goal, indicating, according to principal component analysis, that they're uncorrelated or almost uncorrelated. suggesting that W and ZB are good coordinate or observable choices. But the bottom line here is that statistically, the simple multi-objective AR model explains, in a statistical sense, the stepping data, the stepping statistics that we see with humans. Okay, now, what do these tell us, and what don't they tell us? The stepping regulation is organized around a gem. We can explain the statistical structure we see using these simple task level models. We're not just doing statics, because we're also looking at temporal statistics to characterize error correcting regulation strength. We're not just doing data analysis. It's not just sort of like arbitrary regressions for the heck of it, because it's based on a theoretical framework having to do with minimizing error according to some task level goal. Okay, so it gives us a sort of predictive framework that we could apply and have applied in different experimental protocols to say what we think should happen beforehand when we change the task definition. And then last, this is more speculative, is we're saying it suggests hierarchical motor organization, where there's a low-level control that enables you to reliably just execute a movement, but then there's a higher level control that we call regulation. So at this, it's hard for me to even stick with my own terminology, but we're trying to use the word control for the ability to reliably execute the movement, to just move your arm in any direction you want. And then regulation is the refinement on top of that to achieve a precise task goal. So we think our experimental studies have shown this pretty convincingly. However, everything's at the task level. We're just looking at these observables are just the outputs of the motor system, the neuromotor system. And we've built these regulators completely ignoring mechanics. How could that possibly be? Like, why do they work so well? There's no inertia, there's no F equals ma, there's nothing in there, and that's strange. How is the task level gem? So again, by task level, I mean in robotics you would call it at the end effector level. So for walking, that would be the foot where your steps are taking place. Or the task levels, what are the variables that define task performance? But how are those things represented in the body? There must be some equivalent way that the gem at the task level is pulled back into the body. And then most interesting to me is, are there dynamical consequences of this kind of regulation in the entire system? If you have this so-called gem-aware regulations, for example, stability properties, does it, because what we're talking about, there's no mechanical stability. These simple models are incapable of even shedding light on that. So with that, we go to the modeling efforts. So this is integrated template models and the dynamical theory. So in 1999, Full and Kodacek wrote this paper on templates and anchors. And they proposed this distinction between a template. This is a figure out of their paper. So they're looking at insect locomotion, say, and you have a template is a simple mechanical model that has the essential features observed in the dynamics. And so here they're showing a slip model. And then that would be, but it doesn't have, there's anatomical, you're not paying a lot of attention to anatomical detail or anything like that. But then you could anchor it in principle in a more detailed model that would have correct, joints, limb segments, things like that. And then this is, of course, ultimately would have to be represented by would have to be a model of the full organism. And I think of this in terms of that old joke about turtles all the way down. Really, it's kind of like anchors all the way down. You could take this model and break down it into even more detail. So they're using this term templates and anchors. Now, we adopt this, and Full and Kodacek focused on mechanical models really in their discussion of templates. And I think the important thing is, this is a quote out of their paper: the template is not just an ad hoc simple model. The point is why, because otherwise they would have just called it a model, I think. What they mean by template is that it's really kind of a guiding focus or a target of the control system of the entire system, right? So you should really think of the template as being an accurate representation of what the output behavior of the system should be, okay? Now to this, we're going to add what we call a motor regulation template. Those are our empirically, observed and verified models of stepping regulation around some goal equivalent manifold. And when we put those together, we're calling that an integrated template. So we don't just have a mechanical model, because one thing that's important to understand is in robotics, they can design whatever kind of controller they want. In contrast, we're trying to understand what people are doing, right? So we have observed at the output level or task level what people are doing. Now we're taking that and trying to integrate it into a mechanical template in the Full and Kodacek sense to get an integrated template. And the goal is to show how these apparently overly simplistic mechanics ignoring models we've been using in experiments can in fact be grounded in first principles models. So the first thing we looked at is a powered sagittal plane walker. So this is the simplest walking model of Garcia et al., except it has a toe off impulse to permit it to walk on level ground. And just quickly, this would be the stance leg here, and the angles are defined in this way as shown. This is position relative to some fiducial point on the treadmill. And the model only has it's a point mass model of walking. The legs are massless. The feet are infinitesimal, which is to say massless. So there's only this point mass here. And then when it starts walking, this blue leg will swing forward. And at a certain point, the blue leg will also hit the ground. And that's a transition point. And right before it hits the ground, we apply an impulse. And then you switch you take this, the final angle here, and it becomes, because it's symmetrical, you put a minus sign in front of it, and now you have the initial state for the next swing phase. So the mechanics of a double pendulum with a bit of a inertial degeneracy, because there's no point mass at the second tip. The mechanics is a four-dimensional state space because there's 2 degrees of freedom. However, we're only going to look at this impact condition and construct an impact Poincare map, which becomes a stepping map. And as is known since, I don't know, at least Garcia et al., but probably before that, that reduces to really just 2 state variables. You only need the angle theta and its angular velocity basically in this configuration, okay? This entire picture is infinitesimal. Well, no, that's not true. This one is the swing phase, and then the jump from here to here is infinitesimal, and it's instantaneous, right? There's impact and other things that you have to do, which I could discuss if you have questions. So there's 2 state variables in the stepping map. It's a discrete time dynamics that we're going to look at. And the control parameter or input variable or input parameter is the push-off strength P. Now, we implemented regulators for these. So I am going to try to keep using the word regulator for the thing trying to achieve the goal. And on the left-hand side, and all we're doing, but now we have a complete model of the system, okay? It's a mechanical model with the regulator. So what's happening is, on the left-hand side, you have speed regulation, And what we're doing is we're trying to pick the value of P given any value of V that drives V to the drives the speed to the treadmill speed at the next step. So we're picking P at each step to drive the next step speed to the treadmill speed in one step. And when you do that, you get this piecewise manifold. I will say we're using the word manifold a little bit informally because, clearly it's not differentiable at that kink point here down at the corner. But the point is there's a curve here and there's a curve here. This curve is coming because the system, it turns out, which certainly I would not have predicted. First of all, you'll notice that this magenta line is the goal equivalent manifold, okay? It's not a straight line. We're in the body now, so-called, right? We're in the mechanical body. This is the state space here. This plane is the state space. So here's theta and theta dot at the step, at the transition. And if you're on that magenta curve, anywhere on it, you're hitting the target speed. Now, we also did a position controller, and the manifolds are more interesting looking over here. Oh, by the way, this is just for a specific target speed. I'll show you other ones shortly. Oh, I can see it's 244 already. Okay. So again, I'm just going to say there's one manifold here that is the target speed manifold, and there's this vertical slice that puts a bound on it where you lose control authority. Anywhere on this part here, you're hitting the target position on the manifold. Now, if you look at in the Poincare section, what you find is that we can look at the basins of attraction. This point here is a fixed point for steady gait. The yellow basin of attraction is all the states that asymptotically approach that steady state, with the open loop system as yellow. Position regulated is the blue basin of attraction, and speed regulated is green. So the main thing, since I'm going to run out of time here, the main thing I want to just point out is that the speed regulated system has the largest basin of attraction, meaning you can have disturbances farther away from that steady gait and you'll recover to it. Position isn't bad, but it's not as good as speed. And then the open loop one is interesting in its own right, but I don't have time to talk about that right now. Furthermore, we could look at how the speed regulation, how these different basins of attraction vary as we change the targets, as we change the toe-off force or the target speed, which is equivalent. And one of the things I will point out is that even when the yellow basin disappears because there's a bifurcation and that steady state speed no longer in the open loop system exists, the regulated systems actually are stabilized again on that steady gait. So the regulation and the goal directedness can actually stabilize an unstable gait just by itself. And the last thing I want to point out is this idea of basin shifting, which is something that only we could have got from these simulations and these studies, I should say. So here, let's say you want to be on speed 3, which is this gem here. But somebody shoves you outside of the basin. You get shoved, you're outside of the basin, you are going to fall. However, you can simply, by changing your target speed, you will immediately shift the basin of attraction because there's no real inertia in changing your target speed. You can instantaneously change that. And so let's say you were shoved here, I would change to this speed V5, which I would go to. Then after one step, I could change to a target speed of V4, then a target speed of V3, and I could shift the basin of attraction from step to step in principle so that I could recover from very large disturbances, even ones that take you outside of any given basin of attraction. I don't think anybody has ever proposed anything like this. So it's a mechanism for fall recovery that could occur because of these kinds of regulators. Next, I'm going to go to powered lateral walker, and I think Alessandro, I'm going to kind of jump through this. I won't go. I'm not going to be able, but to go through too much of the detail, but the bottom line is this is now the same walker, except now you're viewing this as waddling from side to side. The legs do not cross over each other, and you're just wobbling back and forth. And we have a six-dimensional extended state space, which is the state space plus the parameter space. And in this case, we find a two-dimensional gem. This is the mechanical state space. This is the parameter space. All of these points are periodic gates that meet target values of step width and step position. And all of these do that. But then if you look at this particular red dot, it would correspond, magenta dot, it corresponds to this entire curve of parameter values. So as you vary this magenta dot, all of those gates satisfy the target step width and position, and they each correspond to a curve. So you sweep out an entire two-dimensional internal goal equivalent manifold of these period one gates. I will skip over this and I'll come right to this last part. So we can run simulations on this. And there's the bottom line here is if we look at in this model, we've implemented the 90% step width control on that model. And we get the same scatter plots that we get for humans. Furthermore, so here's like the position control is weakly. These are the direct control plots. It's very weakly corrected. The step width control is slightly suboptimally corrected. And if we look at in the stepping plane, the position gem and the step width gem, the data is scattered. These three pictures are just like their equivalents in the human data. Furthermore, because it's a model, we can actually say what happens if you change the mixture parameter, and we would predict other things. And I will just say that in separate studies, we've found examples where you get isotropic data clouds like this for reasons that it has to do with lane changing, but I don't have time to go into that. Okay, so what did these things answer about the experiments? What did these answer about the open questions left after the experiments? Well, first of all, we've shown there is a mechanical basis for regulation for the GEM regulation framework we're using in experiments. The integrated template models ground the optimal reticulators in first principle mechanics. The hierarchical controller, even when we embed it in these physics-based models, we get linear update models at the task level, even though the system dynamics is very much nonlinear. And they recover the stepping statistics and fluctuation dynamics observed experimentally. The goal equivalent geometry is mapped into the extended state space of the body. The reason that happens is that for any given state of the system, of the full system, you have to tune the parameters depending on the state. You should expect that to achieve the goal at the next step. It would be state dependent. And that's what so that's why it's in the extended state space. And we've done a theoretical demonstration of self-motion, which I didn't have time to talk about. And then the last thing, dynamical features. Goal-directed regulation can stabilize unstable gates. It can greatly increase large disturbance rejection by increasing the size of basins of attraction. It demonstrates the possibility of task switching to recover from stumbles or shoves that push you outside of a basin of attraction. And something else, which I'm only going to gloss over right now, is the gem in the lateral stepping paper that we have, the modeling paper. We showed that it forms a semi-stable set. We believe this is biologically relevant and it's better than a limit cycle model because a semi-stable set, it's a set of period one gates that all satisfy the same goal. But if you get shoved off of it, you come back to the set, but not necessarily the same gate. And this, I believe, is much more how biological walking works. If you get shoved left or right while you're walking, you reestablish your gait, but it's not necessarily exactly the same gait as before. You might have a slightly different posture or made some other adjustment. Closing thoughts. The hierarchical control schema, it actually models a type of control architecture used in engineering for, say, autonomous vehicles called successive loop closure. The human motor system has a similar inner and outer control, where the outer control would be the motor planning and coordination subsystem. And the successive loop closure lends itself to cascaded models where you could, in principle, don't think this would be hard, this is much more speculative, you could, for example, take any of the elements in our model, and you could go inside of it and make that element, say the hip spring in our model, you could make it the output of an even deeper model of the muscle required for activating that spring. So you could kind of make cascaded models to whatever level of complexity you wanted. And last, successive loop closure conceptually parallels biological motor skill acquisition, where a child learns to crawl, then knowing how to crawl, they learn how to stand, then knowing how to stand, they learn how to walk, then knowing how to walk, they learn how to run. You're taking a previous level of controller development or training, and then you take that and you add another refinement on top of it to do something more precise or different. I want to thank everybody for patiently waiting through my talk. This is John Dingwell, my partner in crime. We've worked on most of this stuff together. Navendu Patel did all of he's an outstanding computational dynamical systems researcher, and he did a lot of the great analysis and our modeling work that I've showed you some of here. And all of the code, by the way, if you look at those papers, all that code is available on Zenodo. So with that, I will end and say thank you to everybody.
Okay. Beautiful. Thank you so much for the fantastic talk. So we have time for some questions.
Can I jump in?
Yeah, Satya.
Oh, there's people here.
Yeah.
Awesome.
Hello, Dr. Dingwell. It's nice to see you again.
Yeah, I'm not Dr. Dingwell, but I'm Joe.
Of course.
That's okay. No problem. Hi. Hi, how are you? Good to see you.
Yeah, I've been well. I've been a fan of your and Dr. Dingwell's work for a long time, although I should admit I haven't been keeping up with your recent developments.
We're all too busy.
Well, I have a couple of questions. Would you say a little bit more about Full and Kodichek's idea of the template? And the reason I ask is I completely appreciate the attempt to move inside the body from the initial work on step lengths and speeds. And the models that you end up using are these double pendulum walking models, or maybe a slip model, which are very, very intuitive from a mechanical engineering or a physicist point of view. So is there something in Full and Kodichek's argument that makes it seem more salient than a physicist's intuition? Why should the body care about this specific or this style of modeling?
Okay, here's my thought. I will say that I find the template and anchor language to be good, but mostly from a almost poetic point of view. I don't find it to be, like, from a mathematical point of view, it's like, what exactly is a template? What exactly is an anchor? The part that I really like about it, though, that made me want to use their language is this idea that it's not just like in engineering and physics, you kind of simplify models, right? But their point, at least my read of their paper, is that their point is that the simplified model, it's not just a simplified model. It's sort of like a target of the more complete system. So that's the first thing. That's why I'm using the language. Now, I think in your second part of your question, there's something that is a deep issue. And I actually think it's kind of one of the reasons there's sort of like sometimes there's a debate between most of the people in motor control and people like me who are doing this kind of work. And it's a legitimate point that I wish we would just talk about. and it's this. I am showing that this compass walker takes steps like a human. Obviously, it is anatomically incorrect. So what we're showing is not that we think people walk like a compass walker. What we're showing is that if you regulate stepping the way people do, you can put it on a mechanical model and it will regulate stepping like people do at the task level. But if you look in our papers, you'll see John and I and Navendu, I'm sure I don't remember where these are in the papers, but I know there's probably a couple times where we said, what we're saying is if it's a robot or a human or an alien from the Andromeda galaxy, if they're regulating 90% step width and 10% position, their stepping statistics will look like this. Now, why does that put what I'm doing in conflict with motor control people? Well, because obviously we're not specifying how neurophysiologically this is happening. It's leaving that open. But why do I think they're complementary and not contradictory?
Mm-hmm.
What we're showing is that the output behavior should be viewed as a boundary condition on the internal model.
Right, like a constraint. Whatever your neurophysiology is doing,
Correct.
it has to
But
show
when you're
these patterns at the
and,
output.
and like energy minimization utterly fails to do that. It's really just not the right framework. So what we're suggesting is, and the other thing is robotics people don't have to worry about that, right? Because they're designing the thing from inside out. But we're trying to figure out what the biological system is doing. And so we do behavioral studies on the whole human being. And so what we're showing is a systematic way to go from the behavioral studies to physics-based models. So is that, was I close to answering your question?
Yeah, I really like that. You have models that explain part of the phenomenon, and that's valuable by itself. And then it is adding constraints to whatever motor control people are going to propose is happening with muscles and activations and whatever.
Right, and furthermore, there's a practical aspect of this modeling work was a legitimate critique of John's and my experimental work was, where's the mechanics? You're saying the people are walking without Newtonian mechanics. Well, we're showing a mechanical system will have the same, like we could take the data output of this system and use our experimental methods on it, and we will be able to interpret what's being regulated exactly the same.
Yeah.
Okay. Yeah. So it's showing that the methodology is not in principle wrong, right? We're showing it's not like so the model architecture is illustrating how that can occur in a first principle setting. Do I think it might be possible to do this with a more complex model like an open sim walking model? Yes, but the fact is it will get very difficult to do.
Yeah, thank you. Can I follow up with a quick second one?
Go ahead.
Yeah. This is all this data, or most of this data, is treadmill walking or over the ground walking?
Treadmill.
Okay. So can you just give a sense for how would this approach be applied if you were walking over the ground, and in particular if there were obstacles in your way, so you have to regulate your stepping or your speed to navigate, step over things, or the slope is changing or something like that, variable terrain?
Okay, well, that's of course going to be a problem, right? But it's not conceptually a problem. It's practically a problem. So as I said in the talk, the goal, it's a hypothesis. I mean, there are some simple kinds of tasks where the goal is sort of determined mathematically, but for walking, there's like so many different ways you could be walking. You have to make a hypothesis. And so once you're walking over ground, you're going to have to decide what is the goal. I don't have data like that, so I'm not even, but do I think applicable? I do. It's just that in practice, it may be difficult. So here, for example, this might be a way to handle it. What if instead of looking at a single person walking, you looked at two people walking together? Then you could say, okay, they want to walk at the same speed. So now you'd have some sort of cross modeling maybe you would do. But I take your point. It's not the first time we've heard the question, what about overground walking? It's a good question. It's a good point. And by the way, it gets even worse if you think about something like dancing. Okay, I don't, I'm not sure what you're going to say the goal is of the dancing. That would be very difficult to quantify.
Yeah, Darichi and Kuo, I think, published something a few years ago where I think they ended up showing that people manipulate their speed if they see that the terrain is going to change some 7-8 steps ahead of them.
Right.
Thank you.
Jonathan Mathis was the person whose name I was blanking on. He's done some really good eye tracking work on people walking on riverbeds over stones. And in his work, it looked like 1 or 2 steps ahead was all people were looking, but it could be context dependent. I mean, that's a very complex environment going from stone to stone, right? Yes. But
Thank you very much.
I think the important thing, the sales pitch I want to make is not that this is easy to implement. The purpose of these model problems is to argue for a certain kind of architecture that the problems have. And I believe there's a very wide range of cases where this architecture will be valid. That doesn't mean it will be easy to implement an experiment. Like for example, the basin shifting idea, I can illustrate it with this toy problem. But how do we apply that to humans? I don't know, because it's hard to figure out what the basin of attraction is for a human, but maybe there are ways to do that.
Okay, so I think we got a fantastic talk, a great Q&A session. So I want to thank Professor Cusumano again for the fantastic talk and everybody for contributing to the presentation. So thank you very much.
Thanks for the excellent questions and again for the invitation.